Okay, so the topic I'm going to talk to you about is model evaluation. And you've done everything, I hope, that I need you to have done in this summer, in the winter school. You've built a model, right? So you've heard about how models are built. So you've chosen the equations for our model, whatever they may be, whether that's the atmosphere or the ocean. We've chosen coordinate systems, which you may have heard about. We've chosen numerical methods, how to solve our equations. We've chosen these things called parameterizations. And now we want to know, is this all working satisfactorily or not? So we put it together, is it working? Model evaluation is a huge field. We can't possibly cover everything in an hour. So I've sort of put the lecture together mainly to give you a few philosophical things to think about, but also a few practical things to think about that you may not, right? Even those of you who are doing model evaluation may not have thought about all that much. And then I'll show you some examples, mostly from our work over the past 10 years or so, to give you a sort of an overview picture. So the first thing you have to ask is, well, what's my model used for, right? Most people think model evaluation is about proving whether the model is right or wrong. If you start thinking about model evaluation that way, you're already on the wrong track. It's not about proving whether a model is right or wrong. There's many kinds of models. They're used in different ways. Some are used to make predictions, right? So we're using weather prediction models, and they make predictions. So we want to know how good the predictions are. So not whether they're right or wrong. We want to know how good they are, how much can we trust them, what can we believe, what can't we believe. Some are used, as we've seen in CMIP, to make projections. Well, can we believe those projections is the obvious question, right? What in those projections is likely right? What in those projections is likely wrong? How would we know? Models are also used as research tools to understand stuff. So you could have a model of El Niño, for instance, right? Well, if your model of El Niño doesn't do El Niño, it's kind of a useless research tool for El Niño, right? So that's a fundamental question. So the fundamental question is not whether the model is right or wrong, but whether it's fit for purpose. So you have to define what's the purpose of this model. And then you have to say the evaluation should evaluate whether the model is fit for that purpose, whatever that purpose might be. Okay, if you want to do research with it, what's the purpose of the research? And is my model capable of actually representing what I want to do research on? If I want to make predictions, is the model capable of doing this? So here's my fit for purpose question for you. Okay, what does fit for purpose mean? Well, imagine your purpose was to get from A to B in the fastest way that you can. Which of these cars would you choose? The racing car, right? Except that I've cleverly hidden with incredibly cleverly put boxes one piece of information that only model evaluation will reveal. So let's do model evaluation. It's actually broken down as well. The guy's sitting there waiting to be told. So the morale of the story is you really need to dig deep to find out whether, well, in this case we didn't have to dig very deep, and it was a rather silly thing of me to do to cover these things. But you really want to do a thorough evaluation what's fit for purpose, and you might end up taking the 2CV there, the 2CV, the French ugly thing, which may not go very fast, but it's the only one on the list that will get you where you want to be at all. All the others are pretty hopeless. I love the one with the tires, the guy with a flat tire having a whole pile of tires on his. It's a lovely photo, I think. So the point of this picture is defining fit for purpose is the task, right? The task of model evaluation is to figure out whether you can use the model for what you want to use it for. Here's some questions that you may want to ask when doing model evaluation. So if you want to apply your model to something like making a prediction, does the model meet the needs of this application? So is it useful to make a 5-day weather prediction? So for instance, just to give you a very black and white example, if you wanted to make a 7-day weather forecast, you cannot use a regional model. Your model has to be global because the weather travels around the globe, and to do something 7 days in advance, it has to be a global model. So a regional model would not be fit for purpose for a 7-day weather forecast, right? It just can't make a 7-day weather forecast because the boundary conditions come from further away. what are the limits of my model's applicability? So what can't I do with my model is a very important question. So for instance, I already used this example. You want to study ENSO, you pick a GCM, one of the CMIP models, and you just use it without checking. You might find it doesn't even do ENSO, or it doesn't do it very well, or it does it for the wrong reasons. Well, then it's not a particularly good model to study ENSO with. And I would say we are not really very good at this as a community to actually check our models for what we want to do with them. Right? So when we pick what's a good climate model for Australia, we often ask the question, well, how does it do temperature over Australia? How does it do rainfall over Australia? Blah, blah, blah. Those are the questions we ask. Useful question. But we all know ENSO is the #1 external mode of, or internal mode of variability that drives a lot of what happens in Australia. So #1 question for climate models to be used over Australia should be, how well do they do ENSO? Right? You can't ignore that question. And they might get the temperature right just by chance, but they may have a terrible ENSO in them. So that's an example. What are the key errors is the next question that influence the model performance. So for instance, staying with ENSO, is it a poor simulation of the trade winds that makes ENSO so bad in this particular model, if we then have a model with a bad ENSO? And then really one of the key things model evaluation should help with and must help with is to try and identify the causes of these errors. And that's, as we will see, the hardest bit and the bit that people do the least when they do model evaluation. But it's one of the most important bits. So for instance, staying with my trade wind example, is we now have to ask, why are the trade winds bad? Is it the boundary layer formulation that causes the trade winds not to be very good? What is the underlying cause? And so most of us stop at 1, 2, or 3, and question number 4 is often not followed up by people. And it's left to the model developers. Here's a limit. So let's talk about some things model evaluation cannot overcome. What are its limits? So one of it is, if you think about it, if you evaluate your model, you need to have an estimate of the truth. Right? What is the truth? Because if you don't have observations of something, you can't evaluate it, right? So there's certain behavior in models that you may want to evaluate, but you have no observations for, or you have no other models that can help you identify it, so you need to know the truth. And I love this little thing, and since Julie gave the CMIP talk, I will be slightly facetious. I show this a lot when I talk about model evaluation. So here's the arrow that points to the truth. This person is coming back from having seen the truth. This person hasn't yet. So this is the naive CMIP 6. I will do everything with CMIP 6 person. And this is the model developer who's actually been and looked what's inside the box. And his hair is standing up and he's completely frightened by the whole experience, right? So that's one way of identifying who these two people are in our world. And here they just say they found some truth under the sofa or behind the sofa. So it's an important limitation, actually, that you might want to think about. There are things in models we cannot evaluate because we don't have information. And then we try and sort of find proxies for it, but it can be very, very difficult evaluating models if you don't have. There isn't a single one-fits-all method for model evaluation, which is why this lecture will become rather complicated towards the end. So we are still in the philosophy part of the lecture. And so really, I think of model evaluation in this little diagram, which I made myself. I'm very proud of it. Oh, I'm not very proud of that, but I can make it go away. See? So I'm very proud of this little diagram. So here's our model. And really, there's 3 phases of model evaluation, and they're all connected to each other. So the first one is, which I call, we are identifying the errors. And that's usually, we apply the model to something, we're making a weather forecast, and we want to know what's right and what's wrong with it. So there's really the right and wrong question. But what works and what doesn't work? So we want to identify errors. Most of model evaluation happens at that level. The next question then is we would like to sort of understand, and so if we only do model evaluation in this mode of identifying errors, all we can do is tuning the model to try and do better, right? Because we have no insight why it might be wrong. All we know it's wrong. And we could tune it, we can play with some parameters in it and try and make the result better, but we wouldn't know what we're doing really. We're just doing it to make a better end result. Now that's perfectly legitimate technique, by the way, in weather prediction. Because I'm pretty sure you don't care why your weather forecast is right as long as it's right. It's a perfectly illegitimate technique in climate prediction because making the model right by tuning it, we have no idea what the implications of that are for running it into the future. And the fact that these climate sensitivities have gone up is because everybody put error sorts in and needed to tune all their models with their new error sorts and still get the trend of the 20th century with much stronger error sort cloud interaction effects and so on and so forth. Hallelujah. Well, there we are. So it's a tuning will not resolve issues. It will simply make the result look better. Okay, it's fair enough. For certain applications, that's all you need. You can get away with that. The next level then is to diagnose the model error, right? Try and figure out what phenomena is the model doing very well, what isn't. I will give you examples for all of these in a minute to make it a bit clearer what I mean with those. And that's really confronting the model with data, more data, and trying to figure out what's going on. The final step, and that's sort of, I would call this model diagnosis, right? So we're really trying to diagnose the various components of the error that we've seen. And the final one, what we really want to do is, of course, we want to resolve something. We want to make something better in the model. And for that, we really need to go down to the process level, right? So where we look at, is the boundary layer well simulated, but more so is the, are the turbulent diffusion coefficients right, or is there a problem with them? Have we done something wrong? Do we use the right formulation? And that's really model development. And good model evaluation, and in many modeling centers this is happening, goes through this loop many, many times. You identify an error that you're annoyed with and that you think is really bad for your application and you need to do something about it. You diagnose where it might come from. You look at what processes may be involved in making it, and you improve those. This last bit is the hardest bit to do, and it's done the least well in the community. Okay, so just for your information, we're not that good at it. Another few sort of more philosophical considerations. You can argue there's qualitative and quantitative model evaluation. What do I mean by this? Well, qualitative means we make a bunch of maps, we look at them with our eyes, and we make subjective assertions about the quality of the model. Both are useful, by the way. There's no judgment here. It's simply I want you to know that people go about this in a quality. The advantage is, in my head, I've accumulated knowledge about something I'm interested in, and I can bring that knowledge to looking at the map. I can machine learn some of that, but not all of it. So really, my brain can interpret these maps very well. And here's an example from work Jennifer Cato did when she was at Monash. The top is the frequency of fronts in era interim, and the bottom is the frequency of fronts in just any front, cold front, warm front, in the multimodal mean of CMIP5. And then you can start looking at this and say, look, there's fewer fronts here in the models in the North Pacific. There's also fewer in the North Atlantic. There seem to be fewer in the Southern Ocean. So there's somehow the model doesn't make enough fronts. And so that's useful information, and you can go on from there. But it's rather qualitative, right? Then there's this sort of more quantitative way where we actually calculate some skill measures. This is an example from CMIP3. It's that old. This is a famous Taylor diagram, and you probably can't see all the little dots, but it doesn't really matter. There's like 6 or 7 variables that are being looked at. Each variable is a different color. Each dot is a model. And this diagram perfect is down here. And the further up you are, the worse the results are. And this is basically just looking at the CMIP3 overall model performance. And you have some really quantitative numbers, and you can say, this variable is better than that variable. But you can also, if you wanted to, identify the models and say, this model is better than that model in this variable, but it's not so good in that variable. So this is a more quantitative way. And then there's a lot of model evaluation that sits right between those. So it's not black and white, but it's sometimes useful to think about this, where we calculate rather complicated measures, but then interpret them with our brain, right? So example on the left, this is the CMIP5 mean rainfall error. multi-model rainfall error. This is just the model rainfall. This is the bias, so just the model minus the observations. This is the absolute error, so negative and positive errors are both counted as positive to just see what's the magnitude of the error, no compensation allowed, and this is the percent error. So these are sort of three different ways looking at the same thing. They are all different measures, so they're numbers that people have calculated, but then we do an interpretation with our brain. A probably more extreme example is this. Not many of you will be familiar with this. It's a depiction of tropical waves, of the strength of tropical waves. The top left is the observations. These guys here are Kelvin waves for enthusiasts. Down here is the MJO. And these are a bunch of climate models in CMIP5 and how they represent this. This is a really complex quantitative calculation to come up with this figure. But then at the end, after we've calculated the figure, we sort of subjectively interpret it. And we say, this model doesn't look too bad. This looks woeful. This is somewhere in between. So it's still subjective at that level, right? We have a bunch of plots. We go in and we make judgments with our heads rather than with numbers. Final sort of philosophical point, at least I think it's the final one. I can't see what the next slide is. Weather versus climate model evaluation. I wanted to bring this up. Most of you here are interested in climate models, but some of you might also be interested in weather prediction. If you recall what the purpose of model evaluation is to figure out whether something is fit for purpose, then in weather prediction, that question, is the model fit for purpose, is relatively easy to answer. Because you make a forecast every day, 3 days later, for argument's sake, or 5 days later, the weather happens, and you can compare. 5 days later, you can make the comparison. And you can do it many, many times. You can do it for many, many forecasts historically, and so on and so forth, right? So from that, you can figure out whether the model is able to predict, say, the pressure patterns or the rainfall patterns, and so on and so forth, and how well, and so on and so forth. So it's very easy to then figure out whether the model is fit for purpose, and you may judge that it's fit for purpose in predicting the flow patterns, the high and low pressure system, but maybe not so fit for purpose of predicting the rainfall. Okay, so that usually is one of the results we find very often, even in the extratropics these days. For climate, this is much harder, because if our purpose for GCMs is to make projections into the future, how do we know what we need to evaluate to tell us which model is making a good projection and which model is not making a good projection? Because we only have the present and the past to look at, right? And so it turns out that errors in the present climate have not been, no one has been able to connect them well to how the model behaves in projections. The top right diagram is illustrating this. This is a study a long time ago by Daniel Klocker and colleagues at Max Planck Institute. And basically, the y-axis is an aggregated error measure of looking over the same sort of 7 variables that we looked at in the previous Taylor diagram depiction of models. So that's the x-axis, and top is bad, and it's normalized between -1 and 1-ish. And top is the model is bad in this measure, and the bottom is the model is good in this measure. The right-hand side is the climate sensitivity of the model, and this is all done with variants of the Max Planck model, that massive perturbations to the parameterizations and so on and so forth. And you can see there's no relationship in this particular ensemble between how well the model performs on these basic indices and what its climate sensitivity is. So that's kind of bad, right? It sort of tells us, even if we knew how well the model is doing now in the current climate, it's hard to predict what its climate sensitivity will be, which is sort of important. So to me, a lot of people conclude from this, wrongly, in my humble opinion. You see how 21st century I am here? Look, IMHO. Right? Very 21st century. I put this in specifically for you guys because I wanted to impress you, I'm sure. I had to Google what I have to put, right? Oh, sorry, I shouldn't have said that. Of course, I'm all over these acronyms. So a lot of people from this conclude wrongly that therefore we don't need to evaluate climate models, right? Because they it's completely, what they do in this particular climate doesn't matter for the future. Well, in my humble opinion, that's not true. It's still a necessary condition that your model simulates the current climate well. if you can't simulate the current or past 100 years of the climate well, then we know for sure you can't do the future right? If you do it well, we still don't know whether you can do the future well. That's the problem. So this has led to has actually led to a new research field, which I'm not a particular fan of, but you might be fans of one day, that is called the field of emergent constraints. And this is where people now specifically look for behavior in the model in current climate that maps into behavior in future climate. And the first study, as far as I'm aware, that did this was Alex Hall study, Hall and Shu, in 2006. And they looked at the seasonal cycle of albedo in regions where there's snow. And they found that if you plotted the seasonal cycle of that in percent change in albedo per Kelvin change in the seasonal cycle, and you plotted that against what models did in climate change, this was in CMIP 3 days. So here's how the models change this albedo in percent per Kelvin. It goes down, of course, because the snow goes away and the darker surfaces win. Then they all fell on a line. So there was a behavior in the models where the seasonal cycle mapped into their climate change behavior. And then, of course, you can say, all right, what's the observed bit in the seasonal cycle? Because we can observe the seasonal cycle. And the observations lie here. And you can see there's, if you sort of close your eyes somewhat, 3 models that do it correctly, right? But you can say, well, most likely the correct behavior comes from those 3 models. That's at least the assertion in this climate, in emergent constraint studies. So you can look this up, and since then, lots more people are, so there's this sort of search for all these measures that map into climate change. And people forget to the fact that the mean rainfall in climate models hasn't improved since 1990, something like that. So 30 years ago, we had certain errors in rainfall. There's still the same errors today. Emergent constraints will not save us. Oh no, there was one more philosophical point, which is actually fun. I'm testing your mathematics skills somewhat now, only a small test. And that is, when you do model evaluation, you will likely use statistical techniques. You will calculate certain numbers that give you an indication of how good a model is. And I just want to put a little warning light up that whenever you do that, be aware of the methods and measures that you use when you look at models. So here's my example. Imagine this sine curve, the red sine curve here, is our observation. We have 2 model predictions for it. We use this one. Model 1 predicts this, and model 2 predicts a flat line. Okay? Now let's calculate, if I asked you to calculate the root mean square error of these 2, what do you think, or before we even do this, which one is the better model, you think? 1 or 2? Why? Yeah, kind of, if you think of this as a ridge and a trough, southern hemisphere, trough and a ridge, if you think of it that way, then the model 1 predicts that, but it has it in the wrong place. So model 2 predicts zonal flow. So that's kind of useless. Now let's calculate the root mean square error. Watch the effects. I've worked very hard on those. Whoa! So the root mean square error for model 1 is 1 in this particular case. What do you think for 2? Will it be higher or lower? Lower. There you go. Boom. Model 2, 0.7. So if we just use quantitative measures and we've chosen root mean square error to look at this particular problem, we would conclude that model 2 is better than model 1. But from a subjective meteorologist's perspective, if these were pressure patterns or 500 hectopascal height patterns, we would have concluded, So what you learn is if you use measures like root mean square errors, which we do, or we use variants of this also in climate model evaluation, smooth fields will always give a better score than rough fields. Which is in part, not entirely, but in part why multimodal means often come out better than individual models. Because one thing you do by making a multimodal mean is you smooth the individual patterns that the individual models are producing into a much smoother field. And smoother fields just give better scores. So some of this, it's not all of the story, but some of the story why multimodal means are performing better in these some of these quantitative measures is simply because they're smoother fields. The Taylor diagram, by the way, is an expression of the root mean square error. I hope you know that. And if you don't, we don't have time. I can give an entire lecture about the Taylor diagram itself. So, but come and talk to me if you're interested. And the other, so the final node, philosophical or broad node on model evaluation, which I think is more useful to take away from this lecture than individual examples, is model observation mismatches, right? They happen all the time and everywhere, and they're really hard to deal with. So that's apples and oranges, and there's the apple saying, well, that question is completely unfair. It would be like comparing us to them, right? And so you really have to be aware that when you look at a model, the model results and the observations are not matching a priori. You need to actually think about whether you can compare the two. The simplest example is if the model results are all area averages over the grid box size of the model, but we can have station observations, for instance, right? So how do you compare a single point observation, a station observation, to something that's an area average? This may not be a big problem for things like temperature, depending on topography and so on and so forth. It can be a huge problem for rainfall, which is very spotty, and a single station may not be very representative for an area average at all. And so your model may look bad only because you have a mismatch between what you're comparing. You're comparing apples and oranges. It's true for almost all real observations, and it's particularly severe when these observations come from remote sensing, i.e. when they come from satellites. You know, there's lots of rainfall data sets, but really behind those rainfall data sets is satellite observations, either done with radars or with radiometers. Radars is the same thing. A radar doesn't measure rain. Radar measures reflected radiation at a particular wavelength, and from that infers what the rain may have been. Now, the climate modeling community has responded to this as much as it could by developing so-called observation simulators. I'll show you what I mean with that in the next slide. But before we go there, I wanted to make one other point. We always say, oh, we can get around this by using reanalysis. And that's great. We love using reanalysis, right? Because reanalysis is gridded, just like our model results are, so it's very easy to compare. They are all area averages. We may have to re-grid them and so on and so forth. It's all true and it's all great, but reanalyses are not observations. They're not observations. They're an optimal blend between a model, another model, and observations. For certain measures, they are the best estimate for a lot of things of what's going on in the atmosphere because they're fully three-dimensional. But their convenience doesn't absolve us from looking at real observations every now and then. Just because it's convenient using reanalyses doesn't make it right. And I have seen people using, for instance, rainfall from reanalyses. That's a big no-no. There's not a single observation goes into making the rainfall in a reanalysis. So all you're seeing is the rainfall from the model that's used to make the reanalysis. So if you use the ECMWF one, you see ECMWF model rainfall. So you're comparing ECMWF model rainfall to whatever it is, your model rainfall. Well, that's not particularly useful. Rainfall is a tough one because we don't really have good observations. Or we have very large variability in between the different observational data sets. But that doesn't mean we should stop and just say, oh, let's not do anything and let's use reanalysis instead. So just be careful when you use reanalysis. Certain things are better than others, and it all depends on how much observational information went into this particular variable that you are interested in. I just want to give you a sense of these observation simulators because those of you who deal with especially clouds, precipitation increasingly, but we haven't got good ones yet. So this is an example for clouds. So imagine you wanted to look at clouds and you want to compare model clouds to observed clouds. Well, all observed clouds are not really observations of the clouds the way the model would make its cloud, right? Either it's a person looking from the ground or it's a satellite looking from above. So one way you can deal with this is you can take your observation, which is usually from satellites, it's a measure of radiation. You can convert it into something that you simulate in your model, like cloud fraction, for instance, right? And that process is called retrievals, and that's sort of a very common technique. And if you use a cloud fraction data set from MODIS or precipitation data set from CMORPH and so on and so forth, this is what happened. They measured radiation, they have a model called a retrieval that actually converts that into the variable of interest, like rainfall, for argument's sake. There's another way you can do this. You can take your model results and you can do what's called an instrument simulator and simulate the radiation that the satellite would have measured. And then you compare the radiation with each other. Or, better still, you then take the radiation and do the retrieval on that radiation, which gives you the model equivalent to what the observations are. And that's what most of these observation simulators are doing. If you ever have to use one, the climate community has built a sort of common tool that everybody uses when they do their observation simulation work. It runs in line. When you run your model, you switch it on and it runs as the model runs and produces outputs. It's called the CFMAP, almost CMAP. The F stands for feedback and C stands for cloud feedback model intercomparison project. Observation simulator package cost. It's been published in 2011. And it does things like, and so here are the instruments that it's covering. And you can see they're mostly cloud-oriented, or they are all cloud-oriented actually. I don't know where we stand with doing this for rainfall. I know some people were working on this. So it does things like, here's a vertical profile of cloud fraction from a model, and then the simulator splits this up into little boxes, and then it calculates the radiation the satellite would have measured for each of those boxes, and then tries to compare that to the satellite observation. Okay, let's go through some examples, and then we're finished. Any questions on the philosophies? We will just go through some examples, and then I'll just show you a few examples for each. Yeah?
So I just wanted to see if I was following right. What exactly mean when you said that the model should predict weather well to be able to predict climate well? Do you mean like short-term prediction?
Well, we'll come back to that. The model needs to represent the current climate well, I said, right? That to me is a necessary condition for it to be considered useful to make future predictions. So the current climate. Now, but I want to take you up on your question. So now you have to define what is the climate. And to me, the climate is the PDF of the weather, okay? And so if you take that, then the model needs to predict the PDF of the weather well. Not in weather prediction, but as you run it for 20 years, we shouldn't just check means and Taylor connections and correlations of this, that, and the other. We should also check what's the weather like around the globe. You know, is the model producing the right sort of variability of rainfall, right variability of high and low pressure systems, and so on and so forth? Because if it isn't, then it's unlikely to do well in the future. The difficulty here is to draw the line. What's good? There is no absolute good or bad here, right? There is a fit for purpose. Is the model fit for purpose is the big question. And it's really hard to answer that question for climate. That's the point I'm making. Because if the purpose is to make a projection, how do we know what's important for those projections to be correct? You know, we've had major climate modeling centers submit models to CMIP 5 with a climate sensitivity of 3 or 4, and now you've seen the NCAR example from Julie. Now they are 5 or 6, right? And it's not just NCAR. There's other models that have gone that way. They can't both be right. And it's no guarantee the new one's better than the old one. No one knows. We just don't know, right? So that's a really, really difficult one for climate. Big research challenge for you guys to figure out, right? Okay, so here's some examples then. This is sort of what I would call application-oriented model evaluation. This is a very famous plot on the left. I love how ECMWF gets away with having stuff outside the graph, actually. I downloaded this. You can download this from their website, so you can get the You know, most of my students would get told off if they gave me a graph like that. I would say, come on, hang on a minute. So this is the evolution of the quality of the medium range forecasts of ECMWF. Over the northern hemisphere is the thick line, southern hemisphere is the thin line. The blue is day, let me get this right, day 3, day 5, day 7, and day 10 in advance, all right? And this is how it's evolved, and you know, it's very application-oriented, but the nice thing about these sorts of model evaluations is you can make these charts of the history, right? You can look at how have things improved over the various model generations, if you wish, or the data assimilation plays a big role in weather prediction as well, of course. Now you go and try and find something like that for climate. You'd be surprised how little there is. I found one because I forced Peter Gleckler to make it when we wrote the 5th assessment report. So you can find one in the 5th assessment report. And this is just a pattern correlation of annual mean rainfall from the CMIP models. And this is CMIP 2, CMIP 3, CMIP 5. And it's gotten a little better, mostly because the really crappy models have disappeared. And the models have sort of converged in this area. Right? So it's incredibly useful to have these very simple measures to chart history, to compare model versions with each other. How does this model version compare to that model version, and so on and so forth. But there's very few of them in climate, partially because this argument that even if this number was good or bad, it doesn't tell us much about how the model will behave in its projections, right? So, but that, to me, doesn't absolve us from looking at the current climate. When I mentioned sort of phenomenon-oriented model evaluation, here's an example from a student of mine, Pallavi Govekar. I think she's still at the Bureau right now, where we wanted to know how well do models simulate the three-dimensional structure of clouds around a cyclone, or around an extratropical cyclone, right? So what you do is you have the tracks of the cyclones, you find the cyclone centers, you make a box around those cyclone centers, and then you make a composite where this box gets, you know, overlaid. Every cyclone gets overlaid with every other cyclone. And then here, this is a nice example because it also comes back to observational uncertainties. The observations we had were a radar from space that looks at clouds, and it so happens that there's two sort of limits from this radar, how much cloud there may have been. There's sort of an upper limit, which is the left column here, and there's a lower limit, that's this sort of column next to it. And you can see there's a difference in the observations. So that brings up another point for model evaluation. If you have more than one observation, many of us, including myself, fall into the trap to try and find the best observation. What's the best one? Let's find the best one, and let's use that for our model evaluation. And you spend years and years and years, and you still haven't found the best one. One other approach is to just use the observations that you trust. There may be, just like there may be models that have easterlies in the extratropics and you want to discard them, there may be observational data sets that you really want to discard because they're not that good. But if you don't know, and if they're all sort of at this point in time equally well established, use all of them. You're using 35 models. What's the problem using 2 or 3 data sets, right? So use all of them and see and use them as the sort of limit. And if the models fall within that limit, within that range, use them as a range. And if the models fall within that range, they're probably okay, at least as best we can tell so far. And if they fall outside that range, well, then they're definitely not okay. So that's what we did here. So that's the range of possible answers from the observations. This is clouds at about 2 kilometers, 4 kilometers, 10 kilometers. And these are the model errors, but this is the error against the high estimate. This is the error against the low estimate. So we see, for instance, for the middle, we can't really tell. Against the high estimate, there's not enough cloud. Against the low estimate, there's too much. Upper levels, same story. But at lower levels, in this region of the cyclone, to the northwest, in the northwest quadrant of the cyclone, the model always underestimates the cloud, no matter whether we use the high or the low estimate. So there we've learned something. And it's phenomenon-oriented because we're not looking at a map of clouds averaged over everything, but we're looking at this relative where the clouds are located relative to the cyclone center, right? So that's this sort of phenomenon-oriented. A really nice approach that you may want to consider if you can is sort of a next step from this phenomenon-oriented one, is what I call a regime approach. So if you were able to divide your world, whatever it is you want to evaluate in your model, into a subset of regimes, the easiest to think about is pressure patterns, right? So you could make pressure regimes over Melbourne, low pressure, high pressure, intermediate, troughs, ridges, and so on and so forth. And there are statistical techniques to do that for you, such as cluster analysis. Self-organizing maps is the machine learning one. If you really want to impress people, do machine learning, you use self-organizing maps. Cluster analysis is machine learning as well, by the way, because it's the machine that determines the clusters, not you. So linear regression is machine learning as well. It's just we're not allowed to call it that. EOFs is another one that gives you regimes or patterns, right? So think of them as patterns. So here's an example where we calculated cloud regimes over the Southern Ocean. We calculated, this was work by John Haynes. We calculated them using a very funky phase space that most of you won't be familiar with, but don't worry too much about it. The phase space is where they are in the vertical and how optically thick they are. And then each of those entries in the histogram is the frequency of occurrence of pixels in a box that have this combination of cloud optical thickness and cloud top pressure. Okay, so where it's black, there's lots of clouds. So this regime is lots of clouds that have their top at about 800 hectopascal and have an optical thickness of about 10. For those of you who deal with optical thickness, is anybody here who optical thickness 10 means anything to? Oh, there's one. Great. No, fantastic.
It's a whole bunch.
Yeah, 10 is quite big, actually. 10 is big. And we have, it goes up to 60, by the way. So some of these. So basically, we use this, we find regimes. It's not the point exactly here what the regimes are. You will see what the point is in a second. And then here's the frequency of occurrence of these regimes in DJF and June, July, August, right? So you can then say, where are these particular regimes? So you see, for instance, the last one, number 8 here, is mostly over orography and mostly over land, and so on and so forth. So that's kind of cool, and you can do that from the observations. Now imagine you can do it from a model as well. Wouldn't that be cool? So then for starters, and this is really just the start of the power of this sort of technique, is you can compare the model's frequency of occurrence and the model's maps where those regimes occur. So this is work by Shannon Mason. He used a particular technique to do this. Let's not get hung up on it. So instead of 8 regimes, he has 11. And you can see where these boxes are black, the models and the observations roughly agree on their frequency of occurrence. Where they are blue, these are regimes that the model simply doesn't like to make. So, for instance, if you take number 8, you can't see it, but I'll read it to you. The observed frequency of occurrence is 10%. The model is 0.1%. So you can already conclude model's no good at making this particular regime. And where it's red, that's regimes only the model makes that are never observed, or hardly ever observed. So this one here is observed 9% of the time, and the model makes it 42% of the time. So there's a nice way of looking at your model error, right? And then you can see that in the maps as well. So this top one is the observed map, and the bottom one is the model map for each of those guys. Don't worry too much about details here. It doesn't matter. Why is this powerful? Well, because you can now relate big other errors that mean errors that you might be interested in into this regime space. And this is what I really wanted to get at, because I really want to sort of put this idea in your head. If you do model evaluation and you want to really look a little bit deeper what's going on, even 2 regimes, rain and no rain, for instance, or high pressure and low pressure, you can already do it with just 2. So here's an error that models have had for a long time. I believe they still have it. This is the error in reflected shortwave radiation. It's expressed as cloud-radiative effect here because it comes mostly from clouds. Over the Southern Ocean, so here's Antarctica, you can see it. Again, we use 2 different estimates of this cloud-radiative effect from satellites. one from a product called ISCCP, one quote from series. In both, within those black dotted lines, we see lots of red and lots of deep red, which means the model is not reflecting enough solar radiation back to space. There's not enough clouds, or if they're there, they're not reflective enough. That's the message here. If you have regimes, what you can do is you can write your cloud radiative effect, in this case, from the observations as a sum of the frequency of occurrence of a regime and its cloud radiative effect, right? Its average cloud radiative effect. Does that make sense? That I can do that? I can just split up my mean cloud radiative effect into 11 contributions in our case from the 11 regimes. Each regime contributes its own cloud radiative effect, but times its frequency of occurrence, right? So if it's rare, it may have a big effect, but it may be rare, so therefore, on average, it doesn't contribute much, and so on and so forth. So if I can do that for the observations, I can also do it for the model, right? It's not very complicated to see that I can do that. So I can write the same equation for the model. And then the error in the cloud radiative effect, which is simply the model minus the observation, which is what we see on these maps here, I can decompose that into 3 terms. And that's just simple math, and it's not very difficult for you to work out. I get one contribution to the error from an error in frequency of occurrence. I get another contribution to the error from errors in the within regime cloud radiative effect. And I get a third contribution, which is the cross term. But because both are deltas, this last one tends to be small. And what we're plotting here is the answer to, is this decomposition from a paper a student of mine, Shannon Mason, published. Here are our 11 regimes. And again, the details don't matter. It's about the principle how to approach this, right? So this is the 11 regimes. This line here is the total error, which is 47 watts per meter square for enthusiasts. And these bars tell you how much each of the regime contributes to this error. Okay? And then the bars have different grayscales. The dark gray is how much comes from frequency of occurrence errors. The next dark is how much comes from cloud radiative effect errors. And the cross term is the lightest one. And you can see beautiful things here. First, you can see there's massive compensating errors. So this regime actually contributes strongly an opposite error. If this regime wasn't in the model, the error would be much worse, right? Because this regime compensates. So that's a very typical behavior of models, that there's lots of compensating errors, right? So that you see a mean error, it's 0, doesn't mean the model is doing things right. It could be there's half the time it's too high, half the time it's too low, but on average it's 0. So another sort of lesson to learn. Mean errors by themselves may be misleading. The other thing this does, it helps model developers, because I can immediately tell, if I want to reduce this error, I really have to work on this regime, and that regime. All the others are kind of small contributions, right? So you're not only providing insight that the model is wrong, which, as Julie said, lots of model developers will already tell you, I know. You know, your rainfall is wrong. I know. What are you going to do about it? Can you help me? Can you help me understand why it's wrong, and therefore help me plot a path forward and how I can improve it? So these sorts of techniques help us do that. Okay, I think I have one more slide. Yeah. The other thing not to forget, if you have to evaluate a model experimentation can be very helpful in model evaluation. So you can run a different set of experiments and do the evaluation again to see whether anything changed. And this can be very helpful. I give you 2 examples. One is a traditional one that most of you will have encountered or seen. That's a sensitivity study. You change something in the model, you change model parameter, change the model formulation, you run the experiment again. And if you combine that with a regime approach, which is what happened in this, is a study by Alex Schudeboom in New Zealand at the University of Canterbury. It's just come out in GIL. And he basically looked at the Southern Ocean cloud error as well in the UM, which is the model that we're using here. And he made dramatic changes to microphysical parameters in the model. And what you see is this is the frequency of occurrence error, this is this cloud radiative effect error. And you see there's one regime that stands out like a sore thumb, number 6. It contributes massively to this error that we are concerned about. And the message from this particular set of experiments is microphysics is not going to solve your problem. This is important. That's a very important finding, right? Because the model developers can now stop working on microphysics for this problem. They can keep working on microphysics, but we know microphysics is not going to solve this. It's just not. I'm the only one who will tell you this. You talk to other people, they will say, oh, it's aerosols, it's microphysics, so on and so forth. The other cool one that I wanted to highlight in model experimentation is, and it relates to your question about running a climate model in weather mode, we can do this. And we do it, actually. So here's a composite arrow in reflected solar radiation from a climate model. That is actually the the UK Met Office model that we are using in Australia as well. Now what they've done is they've taken a bunch of December, January, Februaries and make forecasts with exactly the same model, just 5-day forecasts for a few, for about a month worth of forecasts. And then they ask, what's the error if we do that? And look, it looks exactly the same. Why is this cool? It's cool because now we can take an individual forecast, right? We can take one of them and we can say, okay, we know that this mimics that really, really well. But instead of running 20 years, all we've done is we've run 25-day forecasts or 35-day forecasts. That's much cheaper. We also know that the circulation in a 3-day forecast, 5-day forecast is much closer to the truth than the circulation in a climate model that has run by itself for 20 years. The storm tracks and so on may have shifted. They may all be in the wrong spot. So we know the circulation is much better represented. So we can take a single case and we can do a case study, if you wish, and look at more observations for that particular case to try and figure out what's going on. And if we were successful in doing that, then we can see whether this case improves. Once the case has improved, we can rerun the hindcasts, and only once they have improved do we need to run our model for 30 years again. And we very likely have improved that as well. We don't know. But we can start cheap, and try and fix this one case, then check whether that has affected all the other cases positively, and then run another 30-year simulation. So it's a very smart way of actually isolating problems and solving them and then testing whether your solution works. Okay, summary. I probably don't need to read it. So just as a word of caution, model evaluation is a very broad field of research. Of the hundreds of posters that Julie was talking about they have at these CMIP meetings, almost 80% will be on model evaluation, I would say. We'll have looked at what's working, what's not working in a certain way. And people will have very different techniques. So the main goals, in my view, are to identify and ideally help explain model errors. So the explain is the important part here. Identifying model errors is important if you want to use the model for something, but it's not very insightful usually. You have to go and dig a bit deeper. Often for the question whether your model is fit for purpose, you'd need to do that anyway. For the example we had earlier, if you want to see whether a climate model is good for Australia, not looking at ENSO is a crime, right? You can't just look over Australia because that's not going to be good enough. Because you need to know whether the major influences on Australian climate are well simulated as well. There are a number of issues to keep in mind when you do model evaluation. We talked about model observation mismatches, the effects of the techniques you're using, and so on and so forth. And there are many advanced techniques that aim to connect the model error to its roots, which you may want to consider, such as these regime things that I talked about, and also these targeted model experiments. And with that, we'll stop.